Well, greetings, mathletes, and welcome back. This is going to be part 2 of our partial fraction decomposition lecture, and we're going to look at some special cases of this, particularly the cases when one of your factors has a multiplicity. Well, I guess the roots are what have multiplicity, but one of your factors repeats, basically. You have it's there more than one time. Once you factor it out, you have something like x minus 5 squared or cubed or to the 4th power. And then the other case we're going to take a look at is when the factor itself is quadratic. So you have x squared plus 5 minus 1 or something, and it doesn't factor at all. So you're stuck with that factor. How do you deal with that? So that's what we're going to take a look at today. And it's really not too complicated. More than anything else, it's just a matter of knowing how to set it up. As soon as you have it set up, you're back to the same process as before. So let's go ahead and take a look and get started here. Okay. So the first case is when you have a factor repeats. Okay, so if you have something, and I'm not going to worry about what's in the numerator, so I'm just going to, there's a bunch of squiggly bop in the numerator. But you have a bunch of factors, and then you get to this particular factor, and it's, I don't know. Well, I think I said x plus 5 before or something like that. Let's say we have x plus 5 to the 3rd, right? So this is how you deal with it when you break it down for the partial fractions. You write just that factor by itself, right? And that would be under A. And then for the next variable, it's the factor squared. And then for the next one, it would be that factor cubed. So you take every power of that factor up to the power that's actually in the problem, right? Oh, sorry, 3. So if this was to the 4th power, we would have had one more, which would have been to the 4th power as well. So basically, that's how you break it down. You just write down all of the possible combinations of that factor. So I could have 1 of them, 2 of them, 3 of them. And it just depends on whatever this exponent is, how many we put in there. Okay. Now, the other thing that happens is you have a quadratic factor or something with a higher degree than that. I mean, it could be a cubic factor, a quartic factor. But it basically works like this. If I have something like, x squared plus 7x minus 2, and that doesn't factor, right? And keep in mind, there would be other factors in here. Then, we have all our fractions here that we're adding together. When I get to this factor, when I write a quadratic denominator, what I do is I write a linear numerator. And so it's not just a number by itself. It actually turns out to be an ax plus b, right? So if I have a quadratic denominator, I need a linear factor or a linear numerator. If it had been a cube, like if it was x cubed minus 7x plus 4, yeah, it doesn't matter that I'm missing the x squared there. It would be a quadratic factor. It would be a quadratic numerator. So you'd have ax squared plus bx plus c. So the numerator is always the general form of a polynomial that is 1 degree lower than the denominator, right? That's generally how it works when you have something that's not linear. And even with the linear factors, this is a linear factor. The numerator is a constant, and a constant has degree 0, and a linear factor has degree 1. A quadratic factor has degree 2, and all that stuff. So it's always the numerator is always 1 degree lower than the denominator as far as the factor goes. Not as far as how many times you multiply it in, but as far as the factor itself. So those are the 2 new things that we're adding here. So if I have a repeated factor, that factor is going to show up as many times as the exponent on that factor, and it shows up using every single power of that factor up to the one that's in the problem. Okay, so we have that. What we really need to do is get our hands dirty and actually start playing with it. So I have an example here to play with. And we'll go ahead and start with the multiplicity of roots, or multiplicity of factors. Excuse me. So let's start with this. Actually, let's start with a pen. There we go. So let's try that again. So x squared minus 6x plus 3 over x minus 2 cubed. Yeah, that's supposed to be a 3 there. Why don't I just make it look more 3-like? There we go. Okay, so since that's our only factor, that means it's going to show up. That's going to be the only thing we're messing around with denominators here. The next one would be x minus 2 squared, and the next one would be x minus 2 cubed. And then my numerators, since these are linear factors, these are going to be constant numerators, right? Okay, so that's what we're looking at. And the same thing happens. We multiply across by the common denominator, right? So I'm going to get x squared minus 6x plus 3 is equal to, well, let's just put this all in. If I multiply, I should use a different color. Let's do this. So everyone's going to get multiplied by x minus 2 cubed. I put it too far up. I can't cube it. There. There. Okay, so we multiplied by x minus 2 cubed all the way across, including here, so that cancels. And I end up with, let's see, that'll cancel one of them. So it's a times x minus 2 squared plus, and see, two of those will cancel. So this is b times x minus 2. And all of them cancel here, so it's plus c. All right, so now we need to multiply everybody out and collect our like terms, just like before. So the only real difference here is the setup, right? Once you get the setup down, everything else just follows suit. So we have to multiply that out. So that's a times x squared minus 4x minus 4 plus b times x minus 2 plus c. And keep in mind, too, a lot of this gets done in your head as far as the grouping of all this stuff. So if you can do some of these steps in your head, please do. I'm just writing everything out to make sure we can see what's going on. So that's minus 4ax minus 4a. And then here that would be plus bx minus 2b plus c. Yeah, that's everybody. Okay, so now we need to group these. So let's look at our x squared terms first. Well, all we have is ax squared. That's convenient. And now we need our x terms. So I have one here, and that's all of them. So it's plus negative 4a plus b times x. And let's see, what do I have left? So I got that. So it's minus 4a minus 2b plus c. Those are all my constant terms. Yeah, so this is my, oh, that should be plus. There. We'll do it that way. Okay, so we have this now. So that means we can set up our system. Let's see if I can do this so we have enough room. Why don't I slide across here? That'll make it a little bit, give me a little bit more room. Okay, so now the x squared term first. That's a 1, and so that means any coefficient of x squared has to be equal to 1. So we get our first equation as a equals 1, which is convenient because that's actually one of the values we're looking for. And then we get negative 4a plus b is equal to negative 6, right? And then we get negative 4a, now we're on this part, minus 2b plus c is equal to the last coefficient, which is 3. Okay. Well, this is one that's going to be fairly easy to solve by substitution because we already know A is 1, and this one doesn't have a C. So I can just stick the A in here, find B, and now I can stick A and B in here and find C. So that's how I'm going to do it. So we already know A is 1. If I put 1 in here, that means negative, let's do this, negative 4 plus B is equal to negative 6, which means that B is negative 2, right? If I add 4 over, that gives me B is negative 2. And now that I have those two, I can plug those in here. So A is 1, so this is minus 4. B is negative 2, so that's plus 4, plus C. Oh, that's interesting. What is it? Equals 3. And since that cancels, C equals 3. So now we have all of our numerators, and we can write them in. So that means that our original expression there, the x squared minus 6x plus 3 over x minus 2 squared, can be written as, let's see, A is 1, 1 over x minus 2 plus negative 2 over x minus 2 squared plus 3 over x minus 2 cubed. And if you want, you can actually do this too. Where did I put the, there we go. Since that's a negative, you could do this if you wanted to, and it's perfectly okay to just change that to a negative since that's a negative 2, right? So this is what we're looking at. Sometimes it's more advantageous to leave the negative 2 in the numerator, and that's fine too. So both of those are correct answers, but this is what we're looking at. So let's walk through it again. So the big difference was how we set up our denominators, right? If we have a denominator that has a factor that shows up more than once, then every power of that factor needs to be represented in the partial fraction decomposition. So once we represent that and we get our numerators straight, we multiply through by the common denominator, we match up coefficients to find our system, right? And then once we have our system, we solve it, and that gives us our new numerators. And so that's the entire process. Okay, so that's what happens when you have something show up, when you have a factor that shows up more than once. Okay, so let's look at the next case now. And the next case, I'm going to use a quadratic factor because I think that's what your homework is focusing on. But keep in mind that what I had said about higher powers, the numerator is always going to be 1 power lower than whatever the denominator is. Okay, where did I put the second one? Here we go. Okay. Okay, so our second example is the pen's turned off. There we go. Try that again. 5x squared plus 6x plus 3 over, and you notice this, they're nice enough to factor these for you in a lot of these. There we go. Beautiful. Okay, so looking at this now, we have one factor that's linear and one factor that's quadratic. So the linear factor gets a constant numerator, and then the quadratic factor gets a linear numerator. So this is now bx plus c, right? So there ends up being a little bit more algebra that goes on with these. But the same thing's true. We are going to multiply through by the common denominator, form a system, set the coefficients, equal to get our system, and then solve our system. It really is the same thing. So if I multiply everybody by the common denominator here, boy, that would be a lot to write. So we're just going to imagine this denominator sitting up here. I can see that the x plus 1 would cancel out, and what I get is a times x squared plus 2x plus 2. Over here, the x squared plus 2x plus 2 cancels, and I have bx plus c times x plus 1. Okay, so we're here. So now we just need to distribute everything out and collect everybody together and then go and then start running. So we get ax squared plus 2ax plus 2a. And then here, this is basically just foiling it out. So you get bx squared plus bx plus cx plus c. Right? So that's everybody all foiled out. So let's look at here. The highest exponent we got in here is x squared. So let's start with those. I know my x squareds. I have an a and a b as coefficients. So that's x squared. So I've taken care of those. Now let's look at our x's. So I have, let's see here, 2ax. So that one's taken care of. I have bx and cx. Oh, I shouldn't have wrote the x. So it's b plus c, right? Because I had this. Damn it. Try that again. Okay, so I had this term, and now I've used this term and this term. That's the 2a, b, and c. You notice how I'm kind of just grouping the factorization instead of writing them all next to each other in one line and then factoring it in the next. I'm just looking for everything that has an x in it and putting all those coefficients together. And then the last thing would be 2a plus c, and those don't have a variable, so they are their own thing there. And that's going to be equal to this numerator. 5x squared plus 6x plus 3. Right, so now we need to get a hold of our system. So I'm going to move to the other side here again and see if we can make some room. So we know that a plus b is equal to 5. Right? Actually, let me spread this out more so we can see what's going on a little better. So a plus b equals 5. And then the next one, 2a plus, my handwriting. Okay, let's try that again. 2a plus b plus c equals 6. And then the last one, 2a plus c equals, oh, that should be a 2. No, that is a 3. Okay. Yeah, equals 3. There we go. Now, I want to point something out. If you look at just these last two, you notice the first and the last coefficients are the same. So if I subtract one from the other, all I'll be left with is b. So that's what I'm going to do. I'm going to take this and I'm going to multiply it by -1 and add them together. So that tells me that 2a plus b plus c is equal to 6, and then minus 2a minus c is equal to -3. And that cancels, and I get b. I'm just adding straight down. B is equal to 3. So now I know b. Right? So those are the things I'm looking for, right? A, b, and c. So I just found out b is 3. Okay, so how can I get a hold of other stuff? Well, I know a plus b equals 5. And if b is 3, then a plus 3 is 5. So a is 2. So now I have a and b. All I need to do is get a hold of c, and I can use either one of those, anything that has c in it to find c. I'm going to use this equation since I only have to plug in one thing. We know a is 2, so 2 times a plus c equals 3, which means that 4 plus c equals 3, so c is equal to -1. Right, so now I have everybody. So now I can fill this in and say that this is 2 over x plus 1 plus, let's see, b is 3, 3x and minus 1 over x squared plus 2x plus 2. Right? And so that is my final answer right here. Right? It took a lot of work to get there just to split those two fractions apart, but we did it. So once again, you set it up with the unknown numerators, multiply by the common denominator, set your coefficients equal, right? So you want the x squared coefficients to be equal to x squared coefficients and all that. Once you do that, that sets up your system. You solve your system, take the results of the system and plug them back into your original setup. And that's how you find your answer. Okay, so I want to do one more example, and this last example is actually going to be using both of these. And it's a little bit bigger problem than what we've dealt with, because we actually end up with more unknowns than we've had. So let's go ahead and take a look at the last example. Let's see if I can do this in such a way that conserves, actually conserves some space. Okay, so here's our problem that we want to decompose. Let's try it again. So we got x plus 4 over x squared, where'd it go? Oh, there it is, times x squared plus 4. Right, and we look at this, and the factor x shows up twice. Right, we have two x's there, so that's having one of our factors show up more than once. And this factor is prime because it's the sum of squares, and it's quadratic. So we have a repeated factor and we have a quadratic factor here. So let's play. So the repeated factor, let's see, the first one's going to be x, and so it'd be a over x and b over x squared. Right, so we only have to worry about two of those because it only shows up to x squared. And then for the quadratic factor, since this is quadratic, we need a linear numerator. This is going to be cx plus d. So we have four unknowns this time. They're not really variables. X is your variable. A, B, and C are constants we just haven't found yet. Okay, so what we're wanting to do here, now that we have all this set up, is multiply by our common denominator so we can set up our system of equations. So we end up with, try this again. So we're multiplying by this guy all the way across. It's times x squared times x plus 4. Here, one of these x's is going to cancel. So I end up with ax times x squared plus 4. And then over here, the whole x squared will cancel. So this is now b times x squared plus 4. And then here, the quadratic term, the prime quadratic term is going to cancel, and we'll be left with the x squared. So this is times cx plus d times x squared. Okay, so we just need to multiply all this out and collect everybody together. So let's see, distributing the ax, it gives me ax cubed plus 4ax plus bx squared plus 4b. And then there, and it's plus cx cubed plus dx squared. Okay, so we got all that together. Now let's just group these so we can set things up. So for cubes, it looks like I have two cubes. I have a plus c times x cubed, right? So that's that one and that one. Plus, now we need x squared terms. So we have, let's see, b and d. Okay, so we got that and that. And now terms with x in it. Yeah, it looks like we just have the 1 plus 4ax. That's good. So we use that. And then the last thing is plus 4b. Okay, so there we go. And this is equal to this numerator, x plus 4. Now, you're probably seeing the problem here. There's no x cubed over here, right? Where's the x cubed? Where'd it go? What am I going to do with it? Well, I'm actually just going to put it in. Any terms that are missing that you see over here, you can fill in with 0 times that term. So this is actually 0x cubed plus 0x squared plus all of this. So we're going to set the first two equal to 0. So we get a plus c equals 0. Notice that means that a is equal to negative c. So if I find c, I have a automatically. I have b plus d equals 0, and that one means that b is equal to the opposite of d. So b and d are opposites. If I find b or if I find d, I have the other one, right? Anytime you get either of those, it's the same thing with both of these, right? And then let's see here. So here we have the coefficient of x is 1, and I only have 4a as a coefficient of x. So 4a equals 1. So that's used now. And then 4b has to be equal to 4. Well, this one right here tells me that a is equal to 1/4. And this one here tells me that b, if I just divide by 4, is equal to 1. And since we have this relationship between a and c and b and d, a and c are just opposite signs. So this is negative 1/4, and d is the opposite of b, which is negative 1. And those four things right here together tell us how to break this up. So, in fact, let's switch colors just for celebration purposes. Okay, so we have x plus 4 over x squared times x squared plus 4. And we just found out, let's see, a is 1/4, so this is now 1 over 4 times x plus, let's see, b is 1, so this is 1 over x squared. And then our third term is cx plus d, which would be, let's see here, negative 1/4 c plus, oh, it would be minus, d is minus 1, so that's minus 1. Why did I put c? I think I'm losing my mind, guys. The semester's wearing off. It's almost over. That should be x. Sorry. There we go. Negative 1/4 x over, what's my last term? X squared plus 4, right? And I'll tell you this too. In your homework, a lot of the time, the ones that have more unknowns that you need to discover, the algebra tends to be a lot quicker, just because they just kind of cook the problems up that way, so you don't have to focus on the arithmetic to figure out what the theory is behind things. But do keep in mind, once you get out of this section and you end up using this for other stuff, like there's no guarantee the problems are going to come out nice. You could very easily find that a is equal to 341 divided by 17 or something weird and obnoxious like that. So just be aware of that. But it is, all of these are the exact same thing. You go, okay, let's give them all these denominators and, excuse me, mark the numerator as unknown. Then we just multiply through by the common denominator, collect things by like terms, set constants equal to each other, and solve the resulting system. So it's the same thing every time. What changes is the detail, right? How much work you're putting into getting the setup, and how much work you're putting into, well, honestly, a lot of this is tedious. You're distributing things out, you're solving big systems. There's a lot of arithmetic in this. So you just have to be patient and get through it. So in any case, I think we're done for this section. So that concludes everything I wanted to talk about partial fractions. And in Yeah, we're going to be hitting a couple of little topics after the test. Just things we have to wrap up before the end of the semester. But yeah, other than that, that's the end of our lecture for today. So until next time, keep your pencils and your wits sharp.